I'm going to talk about the BICEP Keck experiment, which is our series of cosmic microwave background polarization experiments, which operate from the South Pole and Antarctica. So there's a picture here of one of those telescopes. So this is the telescope. You can see in the foreground here. This is the bowl-shaped ground screen that it sits within. And behind you can see the horizon and the Antarctic plateau. And the sun is setting. And the 6-month-long Antarctic night is about to commence. So our collaboration is relatively small. We're talking 10 to the 1.5 people. Seen here at a recent meeting at Harvard University. So the downtown Boston skyline in the background there. So we are looking for the signal from inflation, from the gravitational wave signal, potentially from inflation. So the idea is, as you all know at the very beginning, that there would be this burst of exponential hyperexpansion, amplifying quantum fluctuations into the structures that we see in the universe today. So we're looking for gravitational wave signals from inflation, and we're doing it by, sorry. All right, I'll come back to that in a second, sorry. So why are we looking for inflation? What is inflation good for? So it potentially solves the horizon problem. It explains why the CMB is so nearly uniform. It sets up the initial conditions which we need, which empirically pertained at the beginning, at a very early time in our universe. So it solved the horizon problem by positing that a tiny speck of subatomic space became the entire observable universe today. In the process of that hyperexpansion, it dilutes away any initial spatial curvature, and it gives us a perfectly flat universe. So it explains the flatness of the universe. And it also generates an initial perturbation spectrum, which is very close to scale invariant, a flat power law spectrum of perturbations, with NS very close to just slightly less than 1. That's because an equal amount of perturbations are ejected at each step in that exponential expansion. And also, potentially in some grand unified theories, you should have magnetic monopoles. It explains the non-observation of those in the contemporary universe by diluting them away to undetectability. So what we are trying to do is use the cosmic microwave background polarization pattern, which is kind of written in at about 400,000 years after the beginning. We're trying to use that to see the trace signature of gravitational waves coming down from inflation from the very, very early time. So inflation injects gravitational waves, they propagate down through the universe, and they generate at recombination time a particular swirliness, a particular curl mode in the CMB polarization pattern. So we are a remote sensing gravitational wave experiment. That's what we're attempting to do, to see the trace of gravitational waves from inflation as they were at combination time. So this slide's got a lot of words on it. It's the most that I've got. So I wanted to just put into one slide this chain of events that may allow us to detect these inflationary gravitational waves. So the CMB is partially polarized. You can decompose a polarization pattern into the E mode, the gradient mode, or the B mode, the curl mode. The basic lambda CDM model says that there will be E modes, and of course we actually observe those, the high signal to noise. Lensing deflections will generate in flight. They distort that initially pure E mode pattern and give you a bit of a B mode. So that's the basic story. Primordial gravitational waves will make both E modes and B modes, right? That's something that's often not appreciated, but we look in the B modes because that's where the lambda CDM signal is the smallest. That's where the gravitational wave signal is potentially most distinct. Theory gives us a good template amplitude, a good template shape for the gravitational wave signal, but it does not tell us the amplitude. We parameterize that amplitude by this number R, and there are a wide range of inflation theories. The simplest ones we've already ruled out. More complex ones can produce R, which is undetectably small, so we may never detect this thing that we're after. We are on this experimental mission to obtain the best possible sensitivity, and as we do so, we rule out steadily more and more inflation models. So that's the name of the game, to either detect or rule out models. So the CMB power spectra is shown here on a log scale, a log y-axis, experimentalist nightmare, right? So the T signal is already very well studied, very well measured and studied. The E-mode polarization signal is at best a factor of 100 down in power units, in squared units. And a factor of 100 below that is the lensing B-mode signal. So the E-mode signal distorted in flight generates a bit of a lensing B-mode. We're after this primordial gravitational wave signal showed here as the dashed line. It peaks, it has a so-called recombination peak at L of 100. So that is what we're after with our experiments. There is also another peak down here at very low L, the reionization peak. We're not after that. So we're after this elevated peak, we're after 2-degree angular scale. So about 4 times the size of the full moon in terms of angular size. So that sets the kind of the background. Now, what do we do? What's our experimental strategy? We use these small aperture telescopes, these funny little telescopes. I'll tell you more about those in a moment. They're cheap, they're relatively quick to build, and they can have low systematics. We target this 2-degree peak, this elevated peak, and we integrate from our site, our observation site at the South Pole in Antarctica. We concentrate all of our power, all of our experimental sensitivity onto a small patch of the sky, like a 1% patch of the sky. And actually, formally, when you're after a first detection, the smaller the patch, the better, right? So that's actually a strength, not a weakness. And we use scan and pair differencing modulation to make the measurement possible. So, of course, we're in a galaxy. You can visualize this as a nearby galaxy. We're about 2/3 of the way out. Our patch of sky that we choose to observe is, of course, almost maximally out of the plane, right? We want to minimize the amount of foreground emission that we see from our galaxy. There's foreground emission both from cold dust grains, which glow thermally in the microwaves, and from relativistic electrons, which are spiraling in the galactic magnetic field, emitting synchrotron radiation. So this plot is showing on the x-axis observing frequency, and on the y-axis the amount of structure on the sky in both E and B modes. Green is synchrotron ramping down as you come up to higher frequencies. Red is dust coming up as you come up to higher frequencies. So the typical C and B observing frequencies are in the 100 gigahertz range, where there's a joint minimum. The dust gets fainter as you go from a large fraction of the sky to talking about a smaller fraction of the sky. The dust signal goes down. Synchrotron signal also goes down, but not by as much. And you've got some crossover frequency at about 100 gigahertz. That's the sweet spot. So since these different components of the sky emission that we're looking at have different frequency dependencies, as shown here, you can separate them by making maps at multiple frequencies. So this is well known. Foreground removal by multi-frequency observation. And that allows us to go deeper looking for this inflation signal. So the BICEP telescopes have had multiple generations. This is the previous generation. These were about 1.2 meters long. The current generation, about 2 meters long. It's got a 50-centimeter aperture. So this is a low-resolution telescope at these microwave frequencies. But we have very high optical throughput. We observe simultaneously a patch of sky that's like 20 degrees across, a big chunk of this, a large instantaneous field of view. And we can pack a lot of detectors into the focal plane, 2500 at 95 gigahertz in the current generation. And that's the name of the game, is just to get more and more detectors on the sky to push down the sensitivity, to push down in terms of our sensitivity to R. So we use these superconducting detectors, transition edge sensor detectors, as detector which is sitting right on the normal to superconducting transition. They are fed by phased array networks of planar antennas, which are arranged on wafers, on focal plane wafers. So this is an 8x8 array of pixels, each of which itself is a phased array. And then we have, in this generation, this is the old generation, we had 4 of those wafers in a focal plane. Now we have a larger number. In the latest generation, the wafers are bigger and there's 12 of them. So that's the basic detector technology. We can tune the pass bands of the detectors by adjusting the microstrip filter on the wafer. And so we have, here are shown 3 pass bands at 100 gigahertz, 150, and 220. And there you can see that those straddle the atmospheric lines. There's an oxygen line here and then water lines either side of the 150 gigahertz line. So we want to look in the windows of wavelength where the atmosphere is maximally transparent. So why do we go to the South Pole, right? It's a lot of trouble to go to the South Pole, but it is an amazing site for doing these observations. It's high and it's incredibly dry. And so you want maximum dryness to reduce the emission from the water vapor in the atmosphere. It's on the Earth's rotational axis, so we get one day-night cycle per year, which makes for really excellent quality data. There's good support infrastructure, there's power, there's cargo, there's data communication, there's food and accommodation, and there's even very limited entertainment. So it's a great place to do what we do. We've had, as I said, this series of experiments. We had the so-called stage 2 experiments, BICEP 2 and Keck array. These were the smaller focal planes with smaller number of detectors shown schematically on the bottom here. BICEP 2 was just a single frequency. Keck array was multi-frequency, 95, 150, 220. Then BICEP 3, which is still running, expanded the focal plane dramatically to get more detectors on the sky. And then the latest generation is BICEP array, which basically is an array of BICEP 3-like instruments. So that's currently under construction. I'll tell you more about that in just a moment. So these are the maps that we get. So I'm just going to take a huge step. You know, there's the instruments. Here's the output maps. There's obviously a lot of work that goes on in between, but let's skip that. So this is the temperature signal, the total intensity, and then we have Q and U, which are the two elements of the polarization pseudovector, right? So those two scalar fields represent a pseudovector field. On the left-hand side, we have the signal. That's what you get when you just add all of the data together. On the right-hand side, we have a noise realization, which is what we get when we add up the data, flipping the sign of the data as we add up, as we accumulate the data. And so that gives us a measure of the noise which is present in the data, right? So there's that much noise on the right-hand side is in the left-hand side. So enormously high signal to noise at 95 gigahertz on this 1% patch of the sky. If we flip to 150 gigahertz, I'm going to flip back and forth. So that's 150, 95, 150. You can see that 150 covers a smaller patch of the sky. That's because it's from the previous generation instruments. We don't have the new 150 gigahertz data yet, although I'll show you a teaser of that at the end. And so we can see that the signal going back and forth, if you look in the left-hand side column, going back and forth, you can see that the signal remains incredibly constant, right? So the Q and U signals, that's the lambda CDM E mode being measured at extremely high signal to noise. So back and forth one more time. And then going forward, this is now the 220 gigahertz map. And you can see going back and forth that the lambda CDM signal is extremely, is also, you know, present in both maps at high signal to noise. The 220 is noisier, right? So sorry, 220. You can see the noise is higher in the right-hand side maps. And you can also see this structure. Focus on that structure right there in the lower right. You can see that just about at 150, and you don't see it at all at 95. And that is polarized dust emission. So it's sticking up above the lambda CDM E mode. So that's the big problem that we have, right? There's foregrounds in there. So to deal with that, we've made these multi-frequency observations of our own. We also add into the mix the maps from WMAP and Planck, which have measured the whole sky, right? We're just doing this little patch of the sky. They've measured the whole sky. And so we might as well add in what they've measured in our patch, right? So they inform us about the emission at other frequencies in that little patch to some level. Although actually now, as I'll come to in a moment, this external data is becoming less important as our own multi-frequency data increases in sensitivity. So the basic technique is to take all of those maps, both our own and the WMAP and Planck maps, and take cross spectra between all of them, auto and cross spectra between all of them, which results in a huge number of spectra and this completely unintelligible plot. But I'll come back to some zoom ins on particular bits of that plot in a moment. So we then need to confront the data with a model. We're doing that in a rather simplistic way. So we have a parametric multi-component model that contains the lambda CDM lensing expectation, plus 7 parameters to describe the foregrounds, plus potentially R, the thing that we're looking for. So the foreground model contains both dust and synchrotron, both of which have an amplitude parameter, and then each of which has a frequency spectral index parameter. So it describes how that foreground, how the brightness of that foreground varies with observing frequency. And then they also have a spatial spectral index, which describes how the brightness of the foreground varies with L, with angular scale. And then there's a correlation parameter also thrown into the mix. So just to try and convince you that modeling the foregrounds, the dust and synchrotron foregrounds as power laws in L is not a crazy thing to do. These are plots. This is a plot from Planck dust analysis on relatively large fractions of the sky, going from 24% up to 71%. This is a plot from Nicoletta's experiment SPAS, measuring the same thing for synchrotron. So that's showing that also conforms to the power law. The reason it's going up here is that's instrumental noise, which is causing that to happen. So modeling these foregrounds as a power law is not a crazy thing to do, at least. We can get into the details of whether it matters later. So this plot is zooming in on the BICEP Keck frequencies 95, 150, 220, and then this is Planck 353. Blue is B modes, green is E modes. The darker colored panels are the auto spectra, each map crossed with itself. And then the lighter panels are the cross spectra. The black lines are lambda CDM, the lensing expectation here, the lambda CDM E mode here, and the green panels. And then the red lines include dust, which has been adjusted to best fit the data, which is the black points. And so you can see that the data agree with the red lines excellently in all of the panels, right? So that is telling us, and then the extension of that statement is to say the chi-squared is okay. So that's telling us that the model is an adequate description of the data, right? There's no need for anything else but lambda CDM and dust to explain all of this data. So I'm just going to step through these plots that show the outcome of the likelihood analysis. So this is from the so-called BKP analysis, which came out in 2015. So that's BICEP Keck plus Planck, a joint paper that we did with the Planck guys at that time. And we have R, and here we have the amplitude of dust. The gray curve is showing the one-dimensional likelihoods for those two. And then the ellipses are showing the cross likelihoods, the correlated likelihood. These little panels are showing the foreground parameters, the additional foreground parameters. So this is the amplitude of dust. This is the frequency spectral index of dust and the spatial spectral index of dust. So that's how things looked in 2015. As we step forward to the so-called BK14 result, which came out in 2015, we go from the gray lines to the magenta lines. The R likelihood goes down a bit. The peak position goes down a bit. The correlation between the dust amplitude and the R gets less. These curves get curves get more circular. We constrain the dust amplitude shifts up a bit. We have a constraint now on the synchrotron amplitude, although it's peaking very close to zero. We are including priors on the beta D and the beta S, and we're marginalizing over ranges in the alpha parameters, the spatial spectral indices. Then stepping forward to the BK15 results, this is adding in BICEP Keck 220 gigahertz data for the first time. Again, you can see the evolution. The R likelihood curve tightens a little bit. Stepping forward to BK18, this is now the most recent result. We get a large improvement on the tightness of that R constraint, so really squeezing down on the amount of gravitational waves from inflation that can be present. The synchrotron likelihood now peaks at 0, so we're not detecting synchrotron. It's the synchrotron signal is a receding target. As we probe deeper, it just seems to get smaller. So it is pretty small in our patch for whatever reason. We no longer have to put a prior on the beta D parameter. So up until the BK15 result, we had a prior on the beta D parameter, which came from other areas of sky, right? That was saying beta D averaged over some large fraction of the high latitude sky, has some value. So we put that in as a prior. As we go forward to the BK18 result, we don't have to do that. The prior's gone. It's now a wide prior, broad prior. And so we now constrain that with our own data for our own patch, right? So that beta D is now definitely applicable in the patch. Synchrotron receding, are getting more tightly constrained. So what does that tell us about cosmology? So to step through the same series of results now, but plotting the results. So this is what we constrain on the y-axis, the R parameter. And the constraint on NS, which comes primarily from Planck data on the x-axis. Planck also, constrains the amount of gravitational waves. So that's the red contour here. And so this with BKP, we were making that contour moderately tighter in the y direction, but not dramatically. But as we step forward to BK14, squeezing down in the y direction, then going from BK14 to BK15, the Planck NS constraint actually shifted slightly to the left. So to slightly values slightly lower than 1, slightly more below 1. The constraint from B-modes is now really the addition of B-modes, the addition of the BICEP Keck data really squeezes down in the R direction. And then going to BK18, it's a whole new game, right? So now the constraint from B-modes from BICEP Keck is completely driving the constraint on R. And we're really squeezing down. With this result, with this BK18 result, the current best published result, natural inflation, this purple banana here, is now ruled out, as are all of the monomial models of inflation, the orange band here. So with this result, we rule out 2 entire classes of inflationary model. So we can take the data, we can take our own data, and we can decompose it without appeal to those spatial spectral index parameters, those alpha parameters. We can decompose it band power by band power, and we get the black points. So that's just showing our most recent data. It's perfectly consistent with lensing alone, right? There's no need for anything but lensing. This is the foreground clean spectrum, right? So for aficionados out there, this is showing the uncertainty in the elevated band power as the points here that comes from noise alone. So we now detect dust at enormous signal to noise of at least 10 in the power spectrum. We do not detect synchrotron yet in our field, so we're just setting an upper limit on that. So eventually we will, but we're not there yet. So what limits the BK18 result, right? Why is sigma r, this uncertainty on the R parameter, the all-important R parameter, it's 0.009, right? But why, right? If we run on without foreground parameters on simulations which have no dust, then we get 0.007, right? Not much difference. And that's as it should be. It indicates that we've correctly set up our sensitivity at the different frequency bands such that we don't suffer much of a penalty on sigma r due to the presence of foregrounds. If we run on simulations which contain no lensing, however, we get a factor 2, more than a factor 2 improvement. That indicates the sample variance on the lensing signal is now the dominant limiting factor in our experiment. So, and just for interest, if we run on simulations which contain neither foreground or lensing, then we get 4 times better, but 0.002. So that's the kind of raw experimental sensitivity that we have. So this schematic shows in the bottom panel the sigma r, the experimental uncertainty on R, the x's are the published results, BKP, BK14, BK15, BK18. The lines here are a projection forward as we add additional experimental sensitivity. The top panel is showing schematically the amount of experimental sensitivity at the different frequency bands, where red is low frequency, green middle frequency, blue higher frequencies, transitioning from Keck array, the previous generation, to the BICEP array experiment, the next generation experiment. In the middle panel, you can see the map sensitivity, the microkelvin arc minute map noise numbers as they come down. Now, crucially here, SPT3G is coming online. That is a high resolution experiment, which is adjacent to us at the South Pole. And we need that experiment so that we can de-lens, right? At the moment, this lensing sample variance is becoming the limiting factor on our experiment. And we need de-lensing to make further progress. So that's what we're going to do, right? So SPT3G, this large telescope, is making maps in our patch. So making high resolution maps on exactly the same patch of sky. And by using those high resolution maps, one can reconstruct the lensing deflection field, which is present in our patch. And one can therefore calculate what is the false B-mode, what is the lensing induced B-mode that is present in our patch. and then subtract it out. Well, not exactly subtract it out, but account for it anyway. Get rid of it in the analysis. So that's what we're aiming to do. We already have a trial analysis. That's funny. Okay. We already have a trial analysis that does that. All right, so the next generation experiment is called BICEP array. It basically builds a new mount and a whole new set of telescopes to improve the sensitivity. There's a picture of it at my home institution, University of Minnesota. We built it in the high bay there. It's the team that I assembled to do that. And then we broke it all apart and shipped it to the South Pole and reassembled it. We did that in 2019. So we had this 3-month window, the 3-month window during which the planes can fly to the South Pole. And so we had to demolish the old mount, build the new one, and get it all working before the end of the season. So that's the team that did that. Just to show you the instruments. So this is the first of the new instruments operating on that mount, the so-called BA1 BICEP array instrument, which is operating at 30 and 40 gigahertz. It's a bigger, better copy of the previous thing. We also now have, finally in 2023, the BA2 instrument is starting to operate at 150 gigahertz. So that's the second of the BICEP array instruments. You may ask, well, why the big delay from 2020 to 2023? That was because of COVID. COVID knocked us back really badly. It really affected the Antarctic program quite severely. You can see that the enormous number of detectors which BA2 will have when it's complete, thousands of detectors pushing down the sensitivity at 150 gigahertz. So just some teasers. This is the previous 95 gigahertz map that I showed you earlier. If we flip to the 40 gigahertz map now from BA1, you can see in the QU panels on the left there, you can see that the lambda CDM signal, it's lower resolution at 30, 40 gigahertz. So that's why it's kind of blurrier looking, but you can see commonality of the pattern. So we're starting to see the lambda CDM signal at 40 gigahertz. You don't actually see any evidence of synchrotron in there, right? It's the thing to note. It's still lambda CDM dominated apparently in this patch. Going to BA2, the latest receiver, we're at 150 gigahertz. You can see that it's starting, this is just a couple of months of data, and it's starting to see the cosmological signal also. So, preliminary analysis using that 30, 40 gigahertz data is pushing down on the synchrotron. So it just shows here that synchrotron is even smaller than we'd previously showed that it was. So to conclude, BICEP Keck is leading the field in this quest to detect or set limits on inflationary gravitational waves. We have the best published sensitivity to date. I didn't talk at all about systematics control, but people have spent years of their lives on that. And but using the data up to 2018, we're now at sigma R of 0.009. And you can ask, why is the R limit, the 95% R limit, 4 times greater? Well, that's because the R likelihood peaks modestly above 0, right? So that's why those two are not just 2 times the other. For the first time, we don't have to put in any foreground priors from other regions of sky. So that's a step forward with the BK18 result. And we rule out 2 entire classes of previously popular inflation models. So the monomial models and natural inflation now appear to be just gone. All right, they're no longer viable. They're no longer consistent with data. We are continuing. We've built a new mount. We have 2 new receivers running, and the delensing in conjunction with SPT3G is under heavy development. So we're projecting that we can do 3 times better than current using data up to about 2027. And sorry, that's because of COVID, right? It would have been sooner, but COVID knocked us back. Okay, thank you very much.